Newton's law of cooling states that the rate of cooling of a body is proportional to the difference between the temperature of a body and the temperature of its surroundings. Theta is the difference between the temperature of a body and the temperature of its surroundings. We are assuming here that the surroundings are maintained at a constant temperature. In this problem, the temperature of the surroundings is maintained at 20 degrees. So the body might have a temperature, say, T degrees, which we don't know. But theta is the difference between the temperature of the body and the surroundings. So usually the body is at a higher temperature than the temperature of the surroundings. So that's what we're talking about when we're talking about Newton's law of cooling. We're interested in the cooling of this body. So its temperature is higher than the surroundings, so its temperature will cool down until it equals the temperature of the surroundings. So the surroundings are kept at a constant 20 degrees, so that this body will cool down to eventually reach a temperature of 20 degrees. So theta is the difference in those temperatures. So theta is T, that's the temperature of the body, minus the temperature of the surroundings, which is 20. So we're interested in the rate of change of the temperature difference with respect to time. That's d theta dt. That's how quickly theta is changing with time. Newton's law of cooling says that this quantity is proportional to whatever theta actually is. So d theta dt at any particular time is proportional to theta at any particular time. So if we double the temperature difference between the body and the surroundings, we double the rate at which the body cools. So that kind of makes sense, I suppose. Now, the change in theta will be negative because this body is cooling. So as time goes on, d theta will be negative. dt, of course, is positive because time is always increasing. Well, in the problems we do anyway. So we have a negative quantity, d theta, divided by a positive quantity, dt. So this is actually negative, this quantity. So d theta dt is negative, less than 0. So the proportionality constant will have to be negative. So to turn this relation into an equation, we will have to stick in a constant, and that constant is actually negative. That's how we because d theta dt is negative. Theta itself is positive. The temperature of the body is greater than the surroundings. So we want d theta dt to be negative, so we have to stick in a negative quantity here. So we just call the proportionality constant minus k, where k is some positive number. So minus k will be, if k is positive, then minus k is obviously going to be negative, which is what we want. So we want this to be minus k theta to be negative. We are given that the body cools from 80 degrees to 60 degrees in 10 minutes. The temperature of the surroundings is maintained at 20 degrees, which we already have. We want to find the value of k. Now we are interested in getting theta as a function of time, how the temperature difference is changing with time. So we'll have to solve this differential equation. So again, as in all these examples, we have a separable differential equation. We can bring all the thetas to one side and t's to the other side. So we have d theta dt, or sorry, d theta divided by theta equals minus k times dt. So all you do here is divide both sides by theta and multiply both sides by dt. So that means we get theta on the left hand side and t on the right hand side. The k is just a constant, of course. So we can put the minus k with the dt, or we can put the minus k in here underneath the d theta, but it doesn't matter. The next step is to integrate both sides. So integrating 1 over theta with respect to theta, that gives us ln of theta, and we integrate this constant with respect to time. If we integrate a constant with respect to time, we just get the constant times time. So on the right hand side we have minus k times t, and we also have an arbitrary constant c, which we show here on the right hand side. It comes from both sides actually, but we just put the constants together on the right hand side. So this here is the general solution to the differential equation. This gives us the relationship between theta and t. Of course, we don't know what c is, and we don't know what the constant k is either. But we're given some information here. We're given that the body cools from 80 degrees to 60 degrees in 10 minutes. So let's look at the case when the temperature of the body is 80 degrees. So what is theta when T is 80? So T stands for the temperature of the body. Well, theta is the difference between the temperature of the body and the temperature of the surroundings. So theta is going to be 80 minus 20, which is 60. So let's plug the value of 60 degrees in for theta here. So we get for theta equals 60 degrees, we get ln of 60 equals minus k times the time. Now t will be the time when the temperature difference theta is 60 degrees, so I'll call this time T60. We don't know what it is, but I'll just call it T60 just to indicate that we're talking about the time at which the temperature is 60 degrees, and we've the constant C. We could do something similar then for the other temperature. The body cools from 80 degrees to 60 degrees, so when the body is 60 degrees, then we can get theta, that's just 80 minus 60. Sorry, 60 minus 20. Theta is the temperature of the body minus the surroundings. That's 60 minus 20, which is 40. So we do something similar. We apply this formula this time for when theta, the temperature difference, is 40 degrees. So we plug 40 in for theta, and let's say the time at which the temperature difference theta is 40 degrees is T40. We don't know this time. We're not given the times actually. Now we are given in the question that it takes 10 minutes for the body to cool from 80 to 60 degrees, or for theta to go from 60 to 40 degrees. That's 10 minutes. So the difference in these times, that is T60 minus T40, must equal 10 minutes. Remember, we want to get the value of K, so we can use this equation here in these two equations, this one and this one, to find out what K is. The easiest way to do this is to take this equation here and subtract this equation. So take ln of 60 and subtract ln of 40, and we get this here. Then take the right hand side of this equation and subtract the right hand side of this one here. So we're subtracting this equation from this equation down here, or actually vice versa. We're taking this equation and subtracting this equation. So if we take this here, the right hand side of this equation, and subtract the right hand side of this equation, we get this here. We have just this minus this, so the c's will cancel out. So we just take this, subtract this, and take this and subtract this. And we can factorize k out of this right hand side and replace T60 minus T40 with 10. So we can just factorize minus k out of this, and we get T60 minus T40 inside the brackets here. T60 minus T40 is actually minus 10, not plus 10, as I said earlier. Because theta is decreasing, the temperature difference theta is decreasing from 60 to 40. So the time at which the temperature difference is 60 will be less than the time at which the temperature difference is 40. So T60 is less than T40, so this will actually be negative. But you could write it the other way around, of course. You could write T40 minus T60 equals plus 10. Anyway, it doesn't really matter. So we've minus k times minus 10 here. So that gives plus 10k, and then we can solve for k. K is just ln 60 minus ln 40 divided by 10. Of course, we can write ln 60 minus ln 40 as ln 60 over 40. ln 60 over ln 40 is the same as ln of 3 halves. So we get ln of 3 halves over 10, which is 0.0405. Let's look at the official solution for part 1. Now the official solution is done in a different way. What is done is to consider the limits of these integrals rather than just solving the differential equation and getting a general solution. We will actually apply limits here, so we will get definite integrals here. It just makes it easier. Now, the temperature drops from 80 degrees to 60 degrees in 10 minutes. So we'll set t equal to naught, the time naught, when the temperature of the body is 80 degrees. So capital T is the temperature of the body. When the body has a temperature of 80 degrees, the temperature difference theta between the body and the surroundings is 80 minus 20, which is 60. So theta is 60. So corresponding to time t equals 0, we have theta equals 60 degrees. Similarly, when t is 10 minutes, so 10 minutes have elapsed, the temperature of the body is 60 degrees. So capital T is 60 degrees, so theta equals 60 minus 20, which is 40. So the limits of the integral on the right hand side involve the time. So the time runs from 0 to 10. That's a time interval of 10 minutes. And corresponding to the values t equals 0 and t equals 10 are values of theta. Theta equals 60, that corresponds to t equals 0, and theta equals 40, corresponding to t equals 10. So we're integrating with respect to theta on the left hand side. So we just perform the integrals as before, integrating 1 over theta with respect to theta gives ln of theta, but we apply limits, theta equals 60 to theta equals 40, and integrating over here, we're just integrating 1 with respect to time, that just gives us t, or integrating minus k with respect to time, that gives us minus kt, same thing. And so we evaluate these at the limits, so we plug the upper limit in first, put 40 in for theta, then a minus sign, then write this out replacing theta with 60. And on the right hand side we have minus k times 10, and then we have minus k times 0. Well, that's just 0. So as before, we can now go and get k. In part 2 we want to find the temperature of the body after a further 15 minutes. So what I will do is use the method of solution 1 here. So I won't actually write down the general solution. I just use this method where we apply limits to our integrals. So the same differential equation applies, of course. So let's look at a solution to it. It's ln of theta equals minus kt. But let's work out what the limits will have to be for this new situation. So let's look at the integral with respect to time. This time we'll start the timer for the second phase. So the second phase starts out with a temperature of, the body has a temperature of 60 degrees now, because it's already, during the first phase it cooled from 80 to 60. Now it's going to cool by more, of course, over a duration of 15 minutes. So when T equals 0, the temperature of the body is 60 degrees. So we're starting the timer when the temperature is 60 degrees. But of course, when T is 60, it means that theta is 60 minus 20, which is 40. So we're really just interested in what the temperature difference theta is. 60 minus 20 is 40. And we're interested in a time interval of 15 minutes. So T runs from 0 to 15. And we're interested in what this new temperature difference will be. And from this new temperature difference, we can go and find the temperature of the body. Basically, we just add 20 degrees on, we just add 20 degrees onto theta to find capital T, the temperature of the body. So T runs from 0 to 15, and theta, when T is 0, theta is 40. When T is 15, we don't know what theta is, so I'll just call it theta. So we plug in our limits, we put the upper limit in for theta, get ln of theta, minus this with the lower limit 40 in. Over here we plug 15 in for t, and we have to multiply by minus 0.0405. Then we have to put in a minus sign, then we have to plug 0 in for t, but of course when we plug 0 in for t, we just get 0, so we just have minus 0 here, so we can forget about that. Solving this, we get ln of theta equals 3.0807. K here is minus 0.0405. I just plugged in that value for the K in the minus KT. So we have ln of theta. To go from ln of theta to theta, we put e to the power of this number here. And to one decimal place, that's 21.8 degrees. So that's the temperature difference between the body and the surroundings. We're interested in the temperature of the body at this new time. This time is 15 minutes after the first phase of cooling. So the temperature of the body is 20 plus 21.8, because theta is the difference between the temperature of the body and the surroundings. So to get T, we just add 20 onto theta. So we just add 20 onto this to get 41.8 degrees.